Simplification of quantum networks is a necessity. And as you can see, as we talked about, there is a significant amount of complexity, necessary complexity, within a repeater itself. If you look at the network, I've got multiple repeaters and many endpoints, and a lot of potentially fiber optic cables and maybe even free space connections that are being used in these systems. Finding a way to simplify the configuration, the monitoring, and the control, and making changes to these systems is critical. And the best implementation for doing this is a software-defined network implementation or architecture. We've seen this, and this has been proven over 40 years in the classical networking space, where we eventually reached software-defined networking there. And now we're able to apply these concepts and this architecture to quantum networking. So what's necessary, and what are we able to do, and what do we need to do in these kind of systems for these sophisticated quantum networks? Well, to begin with, we require centralized configuration, monitoring, control, and even automation of these quantum networks. This is essential. There's a need to support things like multi-tenancy and roles-based access. So there may be multiple people who are using this network and maybe need to configure the network and make changes to the network. And there also needs to be roles-based. There may be classical networking individuals who have access. There may be quantum networking specialists who need to have access. There may be security teams who need to have access, but each one of those has got to have a unique and specific roles and capabilities that they're able to adjust and view, monitor, and control. This system also needs to facilitate moves, as, and changes within the network. If we add, for example, another memory to the network or an entirely new quantum repeater, we need to be able to facilitate the add of that. If, for example, a site goes away, maybe it's a subsidiary that was sold off, we need to decommission that site and maybe the repeater that was connected to that site. So removing those devices. And all these are very complicated because, again, a lot of them are discrete components that need to look, feel, and act like a holistic, complete system at the component device level and at the network level. There are also quantum network protocols that need to be supported. We saw that they were necessary within these devices, but they're also used between devices across the entire network. Things like entanglement swapping. There's also the need to configure very specific and unique parameters within each of the quantum devices and the components in the holistic system that those devices and components make up. In other words, each of the devices, each of the components within each of these nodes, for example, has very unique configuration requirements and changes that often need to be made on the fly and maybe even in real time. So being able to monitor how those are operating and make the changes with those is critical. Being able to manage this concept of entanglement, both the generation but also the distribution of entanglement across the entire network. And entanglement doesn't happen just once. It's an ongoing capability that occurs and is kept fresh constantly. And entanglement pairs degrade over time and need to be reestablished. So we're constantly creating new entanglements, and we're swapping those entanglements to achieve longer distances from node to node, again, using repeaters with these memory capability. And then, of course, being able to discover different nodes within the system and do network configuration within the system across those nodes. Entanglement generation, verifying fidelity of that entanglement, the quality of that entanglement, and being able to do the swapping of that entanglement is another key. And then being able to support a wide range of hardware devices, components, and systems that are completely agnostic to the type of design that's used, the vendor that's used. So being able to support these hybrid vendor models is key. And even when you look at the memories sometimes can be, as we saw, different platforms, different technologies, and different operational profiles that need to be supported. Then, of course, facilitated a complete network-wide and node-to-node error correction and being able to monitor and evaluate fidelity from node to node and network wide is key. All these things are necessary and are things that are achieved through this concept of a software-defined network architecture that simplifies entanglement-based quantum networks and allows us to operate the wide range and many deployments of quantum memories.